Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cyber Security, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss problem solving on pipelining, arithmetic pipelining. So, in computer organization and architecture, so pipelining is an important concept. So, in general, the pipelining is used to increase the performance or speed of the computer. So the pipelining is a technique of decomposing a sequential process into sub-operations, with each sub-process being executed in special dedicated segment that operates concurrently with all other segments. So that means pipelining means, suppose if we have a larger task, that larger task will be partitioned into various sub tasks. Then all that sub operations or tasks, they are running in concurrently in different segments. So that is called pipelining. So mainly pipelining means, it is a technique of decomposing a sequential process into sub operations. That means a larger task will be divided into various sub operations, and all the sub operations are performed concurrently. So by doing this way, we can increase the performance of the computer. And each segment performs partial processing dictated by the way task is partitioned. The result obtained from computation in each segment is transferred to the next segment in the pipeline. So here you can see the pipeline, how the pipeline processing takes place. So here it is a 3-stage pipeline system. So here if you take three stages are there. This is R1, R2, this is a multiplier, R3, R4 registers, adder, and finally R5. So these are the AI, BI, CI. That means these are the inputs to the registers. So each segment, it has inputs. It has inputs and followed by the some combinational logic circuit. So suppose this is one segment, segment 1, segment 2, segment 3. So each segment, it has some inputs and followed by a combinational logic circuit. So this multiplexer, adder, so these are all the combinational logic circuit. So combinational logic circuit means it was implemented using some the logic gates, and the final result is obtained after the data have passed through all the segments. And each segment consists of an input register followed by a combinational logic circuit. And coming to the problem solving, so first one is a non-pipelining system takes 50 nanoseconds to process a task. The same task can be processed in a 6-segment pipeline with a clock of 10 nanoseconds. Determine the speed up ratio of the pipeline for 100 tasks. What is the maximum speed up that can be achieved? So we need to determine the speed up ratio. Okay. So first of all, see what is a speed up factor. So speed up factor is defined as the ratio of time required for non-pipelining execution to that of the time required for pipelining execution. So the ratio of non-pipeline execution time to the pipeline execution time, that is called, it gives the speed up factor. So from the problem statement, the given data is time for non-pipeline execution. So non-pipeline execution time will be represented with t suffix n, that is equal to 50 nanoseconds. Similarly, the time for pipeline execution per task, it is represented with TP, that is equal to 10 nanoseconds. So the number of stages are already here given, 6 segment pipeline. That means the number of stages that are represented with K. So K is equal to 6. and the number of tasks. So the number of tasks given in the problem is 100 tasks. So the number of tasks represented with small n. So that is equal to 100. So the formula for speed up factor is S is equal to time required without pipelining by time required with pipelining. That is a ratio. So time required with without pipeline. So that will be equal to n. N is the number of tasks multiplied with t suffix n. T suffix n. So that means non-pipelined time required for required. So that is multiplied. And the time required with pipeline will be equal to k plus n minus 1 into Tp. Okay. So let's calculate what is the time required for non-pipeline execution of the task. So that will be represented with n into Tn. So n is 100, number of tasks 100, and the time for non-pipelined execution per task is 50 nanoseconds. So total we will get 5000 nanoseconds. Similarly, calculate the time required for pipelining. So already the formula is given, k plus n minus 1 into Tp. So k plus n, where k is 6, n is 100, and Tp is the pipeline time for execution is 10 nanoseconds. So it gives 1050. So now we can easily find out the speed up ratio. So speed up ratio is equal to non-pipelined execution time, that is 5000 nanoseconds, divided by pipelined execution time, that is 1050. So you will get 4.76. So that is a speed up factor. And the maximum speed up that can be achieved is S maximum is equal to Tn by Tp. So that means Tn is a time required for non-pipelined execution per task, that is 50. For pipelined it is 10. So 0 0 gets cancelled, 5. So that means maximum is 5. Maximum speed up is that we can achieve is 5. And coming to the second one, illustrate the number of clock cycles that takes to process 200 tasks in 6-segment pipeline. So we need to illustrate or find the number of clock cycles that are required to process 200 tasks with 6-segment pipeline. So already given. So n is given. N is equal to 200 tasks. And here k is equal to 6 because k is the number of segments. It is a 6-segment pipeline. So k is equal to 6. So there are 200 tasks to be performed in the pipeline processor. The first instruction or task will be taking 6-segment pipeline cycles to exit out of the pipeline. But the other one will take 200 minus 1 instructions or tasks. Okay, so that's why the formula. Therefore, to complete n tasks using k segment pipeline, it requires k plus n minus 1 clock cycle. This is a generalized expression for n tasks for k segments, and the number of clock cycles required are k plus n minus 1. Okay, so here the number of n is the 200 and k is the 6. K value will be 6. So we need to substitute those values into this expression. So 6 plus 200 minus 1, that is equal to 205. So total 205 clock cycles are required to process 200 tasks with 6-segment pipeline. Coming to the third one. The pipeline of figure has the following propagation times: 40 nanoseconds for operands to be read from memory into the registers R1, R2, 45 nanoseconds for the signal to propagate through the multiplier, 5 nanoseconds for the transfer into R3, and 15 nanoseconds to add the two numbers into R5. So first one is what is the minimum clock cycle time that can be used, and we need to determine a non-pipeline system perform the same operation by removing R3 and R4. How long will it take to multiply and add the operands without using pipelining? And third one, calculate the speed up of the pipelining for 10 tasks and again for 100 tasks. We need to calculate speed up for 10 tasks and 100 tasks. And last one, we need to determine the maximum speed up that can be achieved. So here the figure is given. So let's see how to solve the first one, that is what is the minimum clock cycle time that can be used. So here the figure is given. So total it is a 3 stages are given. R1, R2 registers, multiplier, R3, R4 of registers, adder is there, and R5. Okay, so the given propagation times are 40 nanoseconds for reading operands from memory into R1, R2. That means here it takes 40 nanoseconds for reading operands from the memory, and after reading from the memory, it has to load into the R1 register. So for that it takes 40 nanoseconds. After that, 45 nanoseconds for signal to propagate through the multiplier. So currently the value will be in the R1, R2 registers. So from R1 and R2, it has to pass to R3 register by passing through the multiplier. So for that it takes 45 nanoseconds and 5 nanoseconds for transfer into the R3. Okay, so for transferring into multiplier it takes 45, from the multiplier to R3 5 nanoseconds and 15 nanoseconds to add two numbers into R5. So from here to here it takes 15 nanoseconds. The 15 nanoseconds time is for to add R3 content and R4 register content, and finally once they added, it has to transfer to the R5 register. So these are the various timings given, and the maximum propagation delay among these stages is 45 nanoseconds. Okay, so the maximum time is 45 nanoseconds. So if we allocate 45 nanoseconds to each stage, then it can complete the task very accurately. So the maximum propagation delay 45 nanoseconds plus 5 nanoseconds overhead. That means for storing that value into the next stage. So 45 plus 5, that is equal to 50 nanoseconds. So that means minimum clock cycle time that is usually is 50 nanoseconds. Coming to the second one, a non-pipeline system can perform the same operation by removing R3 and R4. So in a non-pipeline system, it can perform the same operation similar to the previous one, but except by removing R3 and R4 registers. That means this R3 and R4 registers are removed. Then we need to calculate the time required for using the non-pipelined system. How long will it take to multiply and add the operands without using pipelining? So already we know different timings for this performing the pipelining technique. So initially it takes 40 nanoseconds for reading the operand from the memory and loading into the R1 and R2 registers. And after that 45 nanoseconds for to transfer that content from R1 R2 to the multiplier. Now here we are reducing this one. Here from multiplier to R3. Actually it is 5 nanoseconds. So now we are removing this R3 and R4. That's why this 5 nanoseconds will be removed. So from multiplexer to adder or R5, it takes 15 nanoseconds. 15 nanoseconds. So now we need to add this 40 nanoseconds, 45 nanoseconds and 50 nanoseconds. So we are removing this 5 nanoseconds because we are not using this R3 and R4 because we have removed that R3 and R4. So that's why the total time required is under non-pipeline technique, 40 plus 45 plus 15 nanoseconds. So total 100 nanoseconds of time is required. And coming to the third one, calculate the speed up of the pipelining for 10 tasks and 100 tasks. So already we know the formula for speed up factor. So the speed up factor, it is represented with S, that is equal to time required for non-pipelined by time required for pipelined execution. So that is equal to n into Tn. So the number of tasks are 10. So we are considering first 10 tasks. So n is equal to 10 into Tn. So just before we have calculated Tn, non-pipelined execution time, that is 100 nanoseconds, by k plus n minus 1. So we are using 3-stage pipeline technique. So k is equal to 3 and n is equal to 10. So 3 plus 10 minus 1, that is equal to 3 plus 9 into 50. Tp value will be 50. So you will get 1.67. That is a speed up factor when it is doing 10 tasks. Similarly, we need to calculate speed up factor for 100 tasks. 100 tasks. So that is equal to 100 into 100 by 3 plus 99 into 50. So only the n value will change. So in first case we are considering 10. In the second case we are considering the 100 tasks. So with that we will get a speed up factor 1.96. And next one, what is the maximum speed up that can be achieved? So the maximum speed up that can achieved S max is equal to Tn, time required for non-pipeline execution, by time required for pipeline execution. So Tn will be 100 and Tp will be 50. So you will get 2. So 2 is the maximum speed up that can be achieved. And coming to the fourth one, that is consider an instruction pipeline with 4 stages. So we have total 4 stages are there. 4 stages means 4 segments are there. So the segment names are S1, S2, S3 and S4. So total we have 4 stages. This is stage 1, stage 2, stage 3 and stage 4. So in between each stage we have a pipeline register. So because to store that value into that register, we are using this registers. So total we are using 4 registers. So this is first register, second, third and fourth. The pipeline registers are required between each stage and at the end of the last stage. Delays for the stages and for the pipeline registers are given in figure. So here in this figure we can see all the different 4 stages followed by 4 registers. So what is the approximate speed up of the pipeline in steady state under ideal conditions when compared to the corresponding non-pipeline implementation? So we need to determine approximate speed up factor. So see, the segments are separated by the registers or suffix I that holds the intermediate results between the stages. So if you see this block diagram, already we know total 4 stages are there. Stage 1, stage 2, 3, 4. So in between 2 stages we are using these registers because these registers are used to store some intermediate results. For temporary storage purpose we are using these registers. And for each pipeline register the delay is 1 nanosecond. 1 nanosecond. And the delay for the first stage is 5 nanoseconds. Delay for second stage is 6 nanoseconds. And for third 11 nanoseconds and 8 nanoseconds. So the delays are given. For stage 1 5 nanoseconds, 6 nanoseconds, 11 nanoseconds and 8 nanoseconds. So and according corresponding register delay is 1 nanosecond for each stage and the total number of stages are 4. So using this information, we can calculate the speed up factor. So already we know the speed up factor is equal to Tn by Tp. So Tn is the time required for non-pipeline execution, whereas Tp is the time required for pipeline execution. So time taken for to execute n instructions in a non-pipeline implementation. So that is equal to non-pipeline execution means we need to consider all the different stages of the delays. So the delay for first stage is 5, for the second 6, third 11, fourth one 8. So if you add total, we will get 30. So 30 into n, because the number of instructions, so 30n. So the total time required for the non-pipeline execution, that is Tn, that is equal to 30 into n. Similarly, with pipeline technique, the maximum clock period required is a maximum of 5, 6, 5, 6, 11, 8. So that means the maximum we are considering 11, because if we provide 11 11 nanoseconds of clock period to every stage, then it performs the task very well. Okay, so plus 1. So this 1 is for the register delay, and this is a stage delay. So maximum of stage delay is 11 plus 1 register delay. So total 12 nanoseconds. So this is a Tp. So now the speed up is equal to Tn by Tp. So Tn is 30 nanoseconds, 30n into nanoseconds by 12 nanoseconds. So you will get 2.5. So the speed up factor is 2.5. So the slides are prepared from by referring the textbooks M. Morris Mano, Computer Systems Architecture, Pearson, 3rd edition, 2015. And also referred John D. Carpinelli, Computer Systems Organization and Architecture, Pearson, 1st edition, 2001. So in this lecture, we have seen what is pipelining, and also we have discussed various problems that are related to the arithmetic pipeline. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.